Hi everyone! The goal of this video is to teach you about what's called a rational exponent. Before I can tell you what we're going to do with rational exponents, I want to tell you what a rational exponent really is. So when I think of rational exponents, I think of rational expressions, which we learned a rational expression is just writing polynomials divided by each other, so you get a fraction. And that's very similar to what a rational exponent is. A rational exponent, well, it doesn't necessarily have polynomials, it's just another word to say a fractional exponent. So if you were raising something to the 1/2 power instead of just raising it to the 2nd power. Our goal of this video is to analyze patterns to discover the properties for rewriting rational exponents. This video is going to be a little bit different because I am going to ask you to analyze patterns here. In order to do that, I need everyone to take out their graphing calculators, which I'm going to use a graphing calculator that's online. It's called Desmos, D-E-S-M-O-S. You can Google it and use it on your Chromebook if you don't have a graphing calculator or any other kind of calculator readily available. It looks like this if you bring it up correctly. The reason I'm going to have you take out your calculators is because what I'm going to do is I'm going to have you pause the video and make calculations to come up with conjectures before I give away the answer. A conjecture is just another word to say a guess or an idea about what's going on in the problem. So what I'm going to have you do is I'm going to have you compute a to the 1/2 power. And I'm going to have you do this for a bunch of different a values. So I'm going to have you do this for a is 1, 4, 9, 16, 25, and 36. So in your calculator, you'd plug in 1 to the 1/2 power and record what that is over here. Then you do that for 4, 9, 16, 25, and 36 until you're done with all those. And before you restart the video, I want you to make a guess about what a to the 1/2 power really means. And you're going to record that here. So now I want you to pause the video and go ahead and plug all these values in for a here and record what you get and make a guess and then restart the video. Good luck! Okay, I hope you're all being honest and did what I asked you to do because it's so important that you figure out these patterns and learn how to analyze data on your own. If you didn't, pause the video, go back and do it. So you believe me because you don't want to take my word for it, you want to try it on your own. If you do substitute these values in for a, you should get that 1 to the 1/2 gives you 1, 4 to the 1/2 gives you 2, so on and so forth. 9 gives you 3, 16 gives you 4. So in your conjecture, you should be thinking about, okay, when I'm taking a to the 1/2 power, what is that the same as? For example, if you just learned that 16 to the 1/2 equals 4, what else can you do to 16 that would give you an output of 4? And I hope you realize they gave you a bunch of perfect squares, and the outputs are their square roots, because a to the 1/2 power is the same thing as taking the square root of a. I'm not going to write anything in the conjecture. That's for you to write notes to yourself as you're doing the discovery on yourself. I want you to do the same thing, but do it with a to the 1/3. So plug in these values and come up with what a to the 1/3 is equal to, similarly to what we did for a to the 1/2. Okay, pause the video and go. And now I'm back with the answer. So when you did 1 to the 1/3, you should have got 1. 8 to the 1/3 is going to be 2. 27 to the 1/3 is going to be 3, so on and so forth. And I hope you came up with some really good ideas about what this looks like mathematically or what else this looks like. So let's look at one example. When I did 27 to the 1/3, I got an output of 3. So what else can you do to 27 that would give you an output of 3? What operation can you do? And hopefully you were thinking about the last example and came up with that this is the same thing as taking the cube root of a. Okay, the cube root of 27 is what can you multiply 3 times to give you 27? And the answer would be 3. Or what can you multiply 3 times to give you 125? The answer would be 5. Okay, so prediction for a to the 1/4. If you kind of think about this pattern, you should recognize that a to the 1/4 is going to be taking the 4th root of a. So if I did 64 to the 1/4, that should be the same as taking the 4th root of 64. I took the liberty of already plugging this into Desmos, so you can see that they are in fact the same. The 4th root will give you 2.8, and raising to the 1/4 power will also give you 2.8, on and on and on. And how did you come to this conclusion? I want you to think about it on your own, but in math oftentimes you can see common structure in problems that look similar even though they're different. So if this is the 1/2, that makes this a square root. The 1/3 makes it a 3rd root. So notice that the denominator becomes the index of the radical. The denominator becomes the index of the radical. So you're seeing that common structure. Now I want you to try a to the 2/3 and a to the 3/4 and see what happens. And I'll come back with both of those after you've done them on your own. Okay, here are the answers for the computation. Let's talk about what we discovered. So you notice that a to the 2/3 is kind of like a to the 1/3, except it's got a 2 in the numerator. So what I would do is if I'm looking for similar structures, I would compare my answers from a to the 1/3 to a to the 2/3. Now, hopefully you're noticing that 1 raised to any power is still going to be 1. But how does 2 compare to the 4? So the 1/3 power gave you 2, the 2/3 power gave you 4. How does 3 relate to 9, 4 relate to 16? Hopefully you're noticing that to go from this step to this step, you square each of the answers. So I'm thinking, okay, square each of the answers. How does that relate to my problem? Well, if the 1/3 power is the cube root of a, and I have to square my answers, what you're really doing is you're squaring the cube root of a, which that numerator tells you what exponent you're raising it to. I didn't write out the answers for a to the 1/4 for each of these numbers, but if you can kind of look at the structure from above, the pattern will continue. So the 1/4 power would be the 4th root of a, the 3/4 power would be the 4th root of a raised to the 3rd power. So in general, if you have a fractional exponent, the denominator becomes the index of the radical, and the numerator becomes the exponent. This means that for a to the m over n, the root will be the nth root, or the denominator becomes the index, and the numerator will become the exponent you raise it to. So these are equivalent ways to write fractional exponents as roots or exponents, which is how this ties into the last videos. For some examples, we can rewrite any of these problems either using roots or using fractional exponents. So 9 to the negative 1/2 power, you can, again, this is really the same thing as 9 to the negative 1 over 2, just a different way of writing it. So whatever the denominator is becomes the index of the radical. So 2 would be the index, but that's just a square root of 9. Whatever the numerator is would become the exponent. Now, in terms of the negative, you can't have a negative index, like a negative root. That doesn't even make sense. So that negative has to travel with the exponent. Okay. Whereas these problems, they're written as radicals. Can we go backwards and write them as fractional exponents? So this is really 6. It's a square root, so the index is a 2, which becomes the denominator. And it's not raised to any exponent, so how many times is it being multiplied? The answer would be 1 time. So the numerator would become 1/2. Same thing for the 3rd root. The base is 6. The denominator would become a 3. And there's no exponent, so it's being raised 1 time. And then you can simplify this, or you can simplify these. So square root of 9, this would be 3, raised to the negative first. A negative exponent would flip it, so this becomes 1 over 3. So you see how, I don't know if I could do this in my head, but this is something I can simplify without using a calculator. So that's why it's helpful to transform the forms. And this is also confusing because I can't take the 3rd root or the square root of 6, but if I rewrite them as fractional exponents, I can use my exponent rule. When you multiply numbers and they have the same base but different exponents, the rule is that you add the exponents. Now, what's 1/2 plus 1/3? They have to have a common denominator. So you could rewrite this by multiplying this by 3 and 3, this by 2 and 2. So this is really 6 to the 3/6 times, not plus, 6 to the 2/6. Okay, and again you add the exponents, so you'd get 6 to the 5/6. And I couldn't really evaluate that without a calculator before, but if you transform the form, it is something you can evaluate. So that's why being able to go back and forth between these two forms is really useful. It'll help us simplify in the end. And I hope you learned a little bit about looking at patterns from going through this discovery, but if you have any questions about where they came from or where I developed this rule, please come and ask. Have a good night.